One of the problems with most of the testing or of those other statistics that we've done was that they don't actually give us one of those p-values that we really want. So we actually have to do descriptive statistics, which actually give us those p-values, which we can then compare to 0.05 to determine whether or not our data is significant or not. The two main types of tests that we will learn are actually in this class going to be the t-test and the chi-squared. But I'm also going to talk about a couple other ones, and I'm going to have you do a couple other ones too, so you can see how different types of statistics are used for different types of data. Okay, so as we said before, I just want to remind you this, I know we just talked about it, but the p-value is called the probability value. This is the percentage or the percent chance that randomness could explain the results that you actually obtained. The threshold value we will always use is p of 0.05. So we're looking for p-values that are always less than that to determine if there's a significant difference between our data or between a control group and an experimental group, for one example, or between something that we'd expect and what we actually get. Okay. There's this other concept you need to know called degrees of freedom, and I'm going to help you guys out with this throughout the year because it changes depending on the test. But this is a value that deals with the number of comparisons that you actually are making. It's usually the number of data points that you collect minus 1 or 2 depending on what you're actually doing. But we'll talk about that more in class and as I go through some of these different statistics. I have no idea where I got that picture from. I think I typed something to Google about it. Whatever. You have to have a p of less than 0.05. Okay, so the first test you're going to do is a t-test. Now, a lot of you, or many of you, I would guess, probably have done t-tests before. But basically what it is it's trying to compare two means of two data sets as well as the spread that is in them to determine whether or not they are statistically different from each other. So this is a really good test to use if we're testing, for example, the effect of fertilizer on plant growth, because we have a control group that receives no fertilizer, and then we have an experimental group that receives a fertilizer. We can compare the mean plant height of one to the mean plant height of the other one, taking into account the variance, which is also taken into account in the t-test, and you end up getting a p-value out of that, a t-value initially, but then you can convert that into a p-value using a chart, which I'll show you a little bit later. So that t-value you get is a statistic value. So it would be like t equals something, okay? That won't mean anything to you unless you have an actual t-chart. You then determine the degrees of freedom. So let's say you have, again, a sample size of 10. In this case, for a t-test, it's n minus 2, so 10 minus 2, so your degrees of freedom will be 8. And then you compare the two. I'm going to show you what a t-chart looks like in a little bit. So there are two different types of tests that exist, a one-tailed t-test and a two-tailed t-test. If you do a one-tailed t-test, it's referring to, when it talks about tails, it's referring to the outliers on a normal distribution. And that's what we're trying to see. Are we kind of pushing our mean towards one extreme or the other? A one-tailed would test in only one direction. So it would say, like for example, if we know the directionality or the expected outcome is going to be in a certain direction, for example, if plants get fertilizer, we'd expect them to grow more. So they should increase in size. Okay, a one-tailed would be probably a good one to use. But if we don't know if it's going to vary where they get smaller or larger, like there's some effect, and it's like you have all these very normal points, but then in your control group, they're all very close to each other, and then they vary wildly, get a lot bigger and a lot smaller, and that's what you're looking for. You would do a two-tailed test because you're testing for variation in either direction, either smaller or bigger. Okay. So here's showing you that t-chart that I was talking about before. These are your actual t-values that you'll obtain as you look through all this whole part over here. These are your degrees of freedom. So if we said if there's 10, I know don't worry about the arrows and the circles at this point, but we said there was 10 data points, then we do 10 minus 2, which is 8. That's your degree of freedom. And we always say our threshold is a p of 0.05. Let's see, which is right here. Okay, it's actually the p-value with one tail. If we're going to do two tails, you have to use this p-value. and then you go down, and if your value is higher than the value at the threshold point at 8 degrees of freedom, then you can say that you have statistically different means. If your value falls below that, notice what happens to this p-value, it gets higher. That means there's a 10% chance randomness can explain your data, a 15% chance randomness, 20% chance, 25% chance, 50% chance randomness can explain your data. Okay? If you're doing one tail, a little different with two tails. So, if that's the case, your value has to be higher than the threshold value. This means less than a 5% chance, less than a 2.5% chance, less than 1%, 0.5%. So the higher your value, the stronger we know the differences between the two means. An ANOVA, which we're not going to do at all, it's kind of like a t-test, but it allows you to compare lots of different means at once. So we would actually use an ANOVA to test that fertilizer example, because we have 3 different fertilizers we want to compare to a control and each other. So you do an analysis of variance. But that's all it does. You don't have to know how it works, or just know that it exists, because in college you're probably going to have to know how to do that. Correlations are when you have you want to see if there's a correlation between two variables, either a positive or negative correlation. And what a correlation is basically it's a relationship. So BMI and blood pressure, right? You'd expect people that have higher BMI to have a higher blood pressure, and that would be a direct relationship, and there's probably a correlation between the two. And we'd collect data to determine that. You'd collect data from lots of different people, plot each point on a set of axes, and then you would see whether there's a positive or negative relationship between the two. Now, in this case, the values for the stat range from -1 to 1. 0 means there's no correlation. 1 means there's a perfect positive correlation, and -1 means there's a perfect negative correlation between the two. So what you're really looking for in this case, depending on the data you're collecting, is you want a value close to -1 or close to 1. This doesn't really give you a p-value, though. You can get p-values from other tests, like a linear regression, but we're not going to talk about that. We'll talk about it a little bit. So this shows you how you do the math from a correlation. I'm showing you this math just because you can see how complicated it kind of is, but in reality it's not that bad, and you can just do it right on your computer. And I'm going to show that when eventually you do your one of your summer assignments I'm going to have you do. The data is always paired points, so a person, or like you have one person's data and you pair their BMI to their blood pressure. So you're going to get like an X and a Y for that person. Height and IQ, you take the person's height and their IQ and you correlate them. And we do it like 400 more times, as it says here, you know, as many times as you can. The more data you collect, the better, and eventually you can get you can do the stat and actually look at it. So this shows you kind of what it would look like, a strong positive correlation, which this would be kind of close to 1. It wouldn't be exactly 1 because they'd all have to fall in the line to be 1. But this is definitely a strong positive correlation and a strong negative. This is a weaker positive and a weak negative, or a moderate negative, excuse me. There's the weak negative one over here, and then there's no correlation at all with this data set right there. So this would be very close to 0. This would be slightly negative. This would be slightly positive. This would be a little bit more negative. This would be almost close to +1. This would be almost close to -1. All right, this last test is the most important one that you have to know for the AP Biology test. We do it in several different units and use it in different ways. So what the chi-squared test, or goodness of fit test, does is it wants to see if counts data, like number of things, differ from what's expected using probability. So the best example I can give you is if you flip a coin 100 times, you'd expect it to count it going heads 50 times and tails 50 times. And if we didn't get that result, approximately, right, there's some leeway there. We could get 47 and 53. If we didn't get that result, so if we got like 25 and 75, we'd say something is up. That coin is rigged for some reason, because the chance of that happening is so tiny. So that's what the chi-squared kind of tests. Does it follow what probability would suggest, or is something else going on? The way it works is you take the observed value that you have. So how many times did I flip heads? In this case, 47 heads. Minus the expected value, you'd expect 50. You square it and you divide it by the expected, which would be 50, and then you get a value for that. You do the same thing with the other one. You do it for tails. The observed is 53. You expect 50 divided by 50. And then you square that initial part before you divide by 50, and you get a value when you add them together. This kind of shows you the chart down here, gives you a value, and you get a chi-squared value of 0.36. In this case, your degrees of freedom equals the number of comparisons you're making minus 1, not 2, like in the t-test. So you're making 2 comparisons, heads or tails. You subtract 1, and you get 1 degree of freedom. And you use this chart. So if you remember, the value is 0.36 at a degrees of freedom of 1. So I'm going to use the pointer here. So our degrees of freedom is 1. Okay. What is our threshold value? Always a p of 0.05, which is right here. P-value of 0.05. And is our value greater than this value? Ours was 0.36. If I can draw 0.36. Our value is not greater than that. Therefore, what we're basically saying is that probability could explain those results. And that would make sense, right? You could feasibly get 47 heads and 53 tails if you roll them. That's not a very odd result. Okay, but if you try to test this more, I'm going to go back real quick. If instead we got something like 25 and 75, like I mentioned before, if you put 25 here and 75 here, okay, get rid of those. Notice how different they are from what you'd expect. And if you plug them in here, 25, 25, 50, and square that, you get a huge number. And even if you divide that by 50, it's still a big number. So you're going to actually show in that case that it's not what you'd expect if you did it. As you can see, our new chi-squared value is now 25. And if you compare it to the threshold value of 3.84 and a p of 0.05, at a p of 0.05, we're greater than that value now. Okay, so that means that we are essentially we've rejected the null hypothesis. Remember, the null hypothesis is what we'd expect. Okay, or random chance could explain it. In this case, we're way beyond that. So random chance couldn't explain our results. All right, that's it for this particular lecture. I hope it wasn't too painful. And remember, if you have any questions, feel free to email me.